Hello friends, my name is Vikas Verma, and in this video I am going to explain you how you can convert your backtracking solution into a dynamic programming solution, or how you can solve the problem using the dynamic programming approach. In the part 1 of the video, I have explained you how you can solve the problem using the backtracking approach with the 5 important key points that you should always remember while solving the problem using the backtracking. If you don't know how you can solve the problem using the backtracking, I would highly recommend you to please watch my first video, because I'm going to use the 5 important key points in this video as well, because first we design the backtracking solution of the problem and then we convert into the dynamic programming solution with the simple tweaks. Alright. So what is backtracking? In the backtracking, we recursively divide our problem into a sub-problems and tries to explore all the possible paths to find the solution. Right? That's what we learned from the first video. In the dynamic programming also, we do the same thing, but we do one extra thing. That is, we try to find the overlapping sub-problems or the sub-problems that repeats again and again. So what we do in dynamic programming is we store the output of one sub-problem somewhere, so that if that sub-problem repeats again, we use the same output instead of computing that sub-problem again. Alright? That's a bit theoretical, right? So let's start with an example that we have used in part 1 of the video, where the 5x5 grid matrix is given and I'm standing at the position first, that is 0th row and 0th column, and I want to reach to the end of this matrix. Alright. According to the problem statement, I can go either to the left side of the matrix or to the down side of the matrix at a time. Alright. Now we want to figure out how many total unique paths are there in this matrix that is take me from the start position to the end position. For example, that is the one unique way, that is the second, that is the third. Alright. So in 5x5 grid matrix, there are 70 unique paths are there that we want to figure out. Alright. So let's start solving the problem. Just for the simplicity, I'm using a 3x4 grid matrix, and we want to figure out all the possible paths that take me from the starting position to the end position. Alright. From the first video, we have learned the 5 important key points, and the one point was that we should always make a virtual tree of a recursion call stack to understand the problem or to design the problem before writing the code. So in this problem also, we are going to use the same approach. First we design the tree and then we write the code. Alright. But before starting, there was also one point where we need to figure out the starting position of a recursion call stack, or you can say the root from where we want to start. Here we are standing at the 0th row and 0th column, from where we want to start. Alright. So finding starting point is fairly easy in multiple problems. So here we start from the 0th row and 0th column. Alright. Here this first 0 represents row and the second represent column. Alright. Now there was also one point where we need to figure out all the possible paths that can be possible from the current position. Alright. From here, according to the problem statement, we can either go towards the left side of the matrix or towards the down side of the matrix. Here, either we can go from here or we can go here, right? So there are two possible paths from this matrix that we can take. Alright. There was also another point where we need to think what values we need to pass into the next call stack to take the decisions further. For example, let's say this path represents that I'm going towards the down, and this path represents that I'm going towards the left. Alright. So to go towards the down, what I need to do is I need to increment the row and keep the column as it is. Right. So I'll increment the row by 1 and I keep the column as it is. If I want to go towards the left side of the matrix, I need to increment the column and keep the row as it is. So here I need to increment the column and keep the row as it is. Now from from this position also, because right now for this path I'm right here, we can take again the two paths. I can go either to the left or to the down. Alright, so there are again two paths possible there. I can go either to the down. So for the down, I need to increment the row and keep the column as it is. So I increment the row and keep the column as it is. So to go towards the down, I need to increment the column and keep the column. So keep the row as it is. Alright. Now for this path, I reach here. Alright. Now I reach here. Now from this current position, how many paths I can take? Alright. Can I go towards the down? Can I increment the row and keep column as it is? Can we take it? No, we cannot take it. Here another point comes into the picture, that we need to figure out what is our base condition or what is our constraints where we want to stop our program to go further. Alright, here we cannot go out of the matrix, right? So that's one of the base conditions where we want to stop our path to go further. So right here we cannot go. There is no path, unique path, that will take me to the end from this position, right? So if there's no path, what I'm going to do is I'll simply return 0. That is, there's no path from this position, is there, right? So let's explore the other paths. Alright, now from 2, 0 position, I can go towards the left, right? I can go towards the left. So let's increment it. From this position, can I go towards the down? No, I cannot go towards the down. I cannot go. I can only go towards the left side of the matrix, right? That is 2 and 2. Alright. Again, from the 2, 2 position, I cannot go towards down, but I can take the position towards the left, right? I cannot go 3, 2. That will take me out of the matrix. But I can take 2 and 3. Alright. Now, this will also return 0 and this will also return 0. Now, 2, 3 is the end position, right? We have reached to the end. So here we also stop our recursion stack to go further because we have reached to the end. We find the first unique path. That is, first we go down, then left, and then again left. That's our first unique path. So if we find the unique path, we can simply return that yes, we find the unique path by returning 1. Yes, we find the unique path. Alright. Now our recursion stack go again upward. But there's also one important thing that you need to understand at this position. That is every time when you go towards the left, you're trying to towards the down, you're trying to finding all the possible unique paths, right? That can be possible when you go towards the down. And when you go towards the left, you're trying to find all the possible unique paths that you can get when you go towards the left side of the matrix. Alright. So as this is returning total number of unique paths when you go towards the down, and this is returning total number of unique paths when you go towards the left, you need to add both of the result to give the final result, right? So the same thing we need to do in every step, right? So here, if we go towards the down, we are getting 0, and if we go towards the left, we are getting 1. So we return the total of these, that is 1. We return 1. Here also, we are getting 0 from the down and 1 from the left. So we return 1 to here. Alright. Same here for 2, 0. Right. Now, we haven't explored all the possible paths from the 1, 1 position. So now we will going to explore all the possible paths from this position. From the 1, 1, I can go towards down, and also I can go towards the left side of the matrix, right? Let me make some space here. I can go towards down. Okay. I can go towards down, that will be 2 1, and I can go towards the left also, that is 1 and 2, right? From 2 1 I cannot go towards down, I can only go towards the left side of the matrix, that is 2 2. Alright, from 2 2 also I cannot go towards down, I can only go towards the left, that is 2 and 3, right? So from 2 3, as we reach to the end, we will going to return 1 from here, and as there is no path, it will return 0. So this path will also return 1, and this path, again there is no path here, that is 0. If we add them, we will get 1 from this position. Now we need to explore now for the 1 and 2. From 1 and 2 I can also go towards the down and towards the right. If we go towards the down, we will get 2 2, and if we go towards the left, then we will get 1 and 3, right? From 2 2 I can only go towards down, I cannot go towards the left, right? Because it will lead me out of the matrix, right? From here we will return 1, from here we will return also 1. From 1 3, how many paths are possible? I can go towards the down, that is 2 3, but I cannot go towards the left, because from this position I will go out of the matrix, it will become 1 and 4. Alright, so that will again return me 1, and that will return me 0. Alright, if we add them, this will return also 1. Now from the 1 2 position, from here there are 2 paths possible. I can go towards the down or towards the right, both are returning 1 1, so we will return 2 here after adding both the path. And from here also, if from 1 1 position, if we go towards down, we get 1, and if we go towards left, there are 2 paths, so we will add them and return 3 here. Alright, from here we return 4. So now we know that if we go toward down, there possibly the 4 unique paths will be there that take me towards the end of the matrix, right? Now we need to solve same thing for the left side of the matrix. So because there are a space crunch here, so that the steps are same, so that will actually at the end return 6. There are 6 possible paths if you go towards the left. You can do it by yourself later also. Now finally you will get 10 as an output. There are 10 unique paths possible for this 3 to 4 grid matrix. Alright, now this is the solution for your backtracking approach. Alright, now we need to think that for the dynamic programming, is there any overlapping subproblem or the subproblems that repeating again and again? Alright, if you closely look into this solution, you can see that let me use a different marker. You can see that from position 2 1 we are repeating the subproblem again, like 2 1 and 2 1 repeating again. Alright, also is there any? Yes, 2 2. 2 2 is also repeating multiple times, right? Also, is there any unique path that is any subproblem that is repeating again? Okay, let me if we explore this path further, if we go towards the down, this will give me 1 and 1, right? And this will give me 1 and 2, right? If you closely see, 1 1 was also repeating again, right? Now we find the overlapping subproblems or the repeating subproblems in this design. So here we know that now we can use the dynamic programming to solve this problem. Now how we can use the dynamic programming? Here we know that for the 2-1, we have already computing all the possible subpath that can be possible from this position, right? So why we are repeating this thing further? Same goes for 1-1. If we are already computed all the unique paths for 1-1, that is 3, why we are computing for 1-1 again? We can simply store this 1-1 result somewhere and return 3 directly from this path instead of computing further, right? Now, how much computation we have secured? We have secured that many of computation for 1-1, right? You can see that how much optimized we have made over this design, all right? So to store the output of any given current state, what data structure we can use? We can use the two-dimensional matrix where each cell represents a unique row and column, right? So this 2D matrix is very suitable for this example, all right? Now let me walk through from this example and see how this 2D matrix is helpful in dynamic programming or in this problem statement. So in the dynamic programming, when we go towards any path, we first check whether there is any computed output is there already in the DP matrix or not. All right, 1 0, we haven't computed anything for 1 0, right? So we will move further. All right, from 2 0, again there is no output. We'll move further from 2 1, from 2 2, and from 2 3. There is no output. We will move further. From 2 2, we actually return the actual output, right? That is 1. So as there is no output here, we store the first possible output that we can get from 2 2, right? That is 1. From 2 1, we also get 1, right? So we will also store the output 1 when we come out from the 2 1 recursion stack, all right? Or 2 1 recursion subproblem. From 2 0, also we are returning 1. Now when we reach at 1 1, we again check whether we have computed the output of the 1 1 yet. No, we haven't computed yet, so we will move further. We will reach to 2 1. We will see that, okay, have we computed the output of 2 1 already? Yes, we have computed already the output of 2 1. So we won't go further to compute the output of 2 2 and 2 3. Again, we just simply return 1 from this subpath. All right. So we return simply 1 here. Now we explore other path from 1 2. Sorry, 2 1 is already there. Yes. From 1 2, have we computed already? From 1 2, no, we haven't computed yet. So we'll move further. We'll see. Okay, for 2 2, yes, for 2 2 we have already computed the value that it will return 1, right? So we just simply return 1 instead of computing this subproblem again, right? And that will, from 1 2 we will get 2. From 1 2 we will get 2 here. From 1 1 we will get now 3. All right. Now 1 0 will return 4. So you can see that when we go downside of the matrix, we will get 4 unique paths. All right. You can see the pattern here, right? So when we try to explore this path, and when we reach to 1 1, we will check that whether 1 1 is already computed. Yes, 1 1 is already computed. We will return 3 directly instead of computing all this subproblem again, right? That's how we can use the dynamic programming to solve the problem optimally. All right. So now we can. Now this is the design for the dynamic programming solution, but there are multiple kind of dynamic programming approaches there as well. So before writing the code, let me explain you this approach quickly so that you can understand these things when you search from Google. All right. So this approach actually is the top-down approach or the memorization approach of the dynamic programming. Why it called top-down? Because from the top level we have decided that, okay, if we get all the possible paths from down or all the possible paths from left, we just add them up and give the result, right? And same thing we do in every recursion call set. We decided that what we will need to do, right? So we are going from the top to down to solving the problem here, right? So that's why we call the top-down approach. And why memorization? Because at every step we are memorize the output somewhere, right? So that's why we also call it memorization approach. But there's one more approach is there for dynamic programming, that is bottom-up approach. In the bottom-up approach, what we actually do is we first compute the bottom result or bottom subproblems, then we compute the top subproblems. All right. In the bottom approach, first we compute for 2 2, then we compute 1 3, and then 1 2, and then 1 1, and then we go slowly upward to find the result. All right. In the bottom approach. So if you want to understand the bottom up approach as well, please give it a comment below. I'll make a video for this approach as well. All right. For now, I'm going to quickly give you some differences between the top-down and the bottom-up approach so that you can just understand when to use when. But if you want to understand everything in detail, please let me know in the comment below, all right? Because otherwise this video will go really very long, all right? So let me explain you some differences, all right? If you're a beginner, all right, or you have just started understanding the dynamic programming approach, I would highly recommend you to first go with a top-down approach only, because in that you can easily understand that what is going on in the recursion call stacks. All right, it is really very intuitive. All right, but you have seen that many competitive programmers mostly prefer the bottom-up approach instead of the top-down approach. Why? Because bottom-up approach is slightly better than top-down approach in terms of time. Actually, although the time complexity in terms of bigger notation would be the same for both the approach, but because in the top-down approach we usually come up with the recursive approach, and we are calling the recursion call stack again and again. So calling the call stack again and again, it's slightly taking more time instead of iterative solution. Sorry, as compared to the iterative solution, right? So in the bottom-up approach, we can easily come up with a iterative solution. All right. So that's why mostly competitive programmers prefer bottom-up approach instead of top-down approach. All right. There are a few more differences. For example, let's say when your recursion call stack is really very deep, that goes up to, let's say, 10 to the power 6, you will get the stack overflow exception, where all the stack will get filled, and your computer don't have enough stacks to do computation further. You will get a stack overflow exception. All right. This exception is called differently in different programming language. In Java, it's called a stack overflow exception, actually. So, but in the bottom-up approach, you won't get stuck in the stack overflow approach because you can easily come up with a iterative approach as well, right? And also there one more slightly difference is that in the recursive top-down approach, understanding the time complexity in terms of bigger notation is slightly tough. But for the iterative approach, in the bottom approach, you can easily come up with a time complexity, or you can easily understand the time complexity of your program. All right. Although time complexity would be the same for both the approach, but it's like how you derive it. Okay. You can easily derive in the bottom approach. All right. So let's start solving the problem using the backtracking approach first, and then I'll let you know with just a simple tweak how you can convert your backtracking solution into the dynamic programming solution very easily. All right, so let's start writing code. Let's call our method unique path. All right, now we need to think that what all the parameters that this method will require. Okay, here in this tree, for every recursion call stack, we need one parameter that represents row and one parameter that represents a column. All right, so the same thing we would require in this problem statement. All right, and we also require two more variables, okay, that let me know that how much the size of the matrix is, like how much the size of the matrix, right? For example, let's say in the previous question we were solving the problem for the 3 into 4 matrix, right? Right here, let's say 3 represents m and 4 represents n. That's the size of the matrix. So the same thing, we just need to pass in every call stack so that we can take some decisions. For example, when we go out of the matrix, we need to check what is the maximum length of the row and the column, right? So that's why we just require two more variables, all right, in every call stack. Now we are done with the required parameters. Now we need to think that in every call stack, how many paths I can take. Let's say from here I can either go towards the down or towards the left side of the matrix, always, right? So there are always two unique paths there, right? So here the code for that. All right, here one time we are calling recursion for to go towards the down and one to go towards the left side of the matrix. All right, now we also need to think about what values will be required in the next recursion call stack. Here we are incrementing the row every time when we go towards the down and keep the column as it is, and if we want to go towards the left, we keep the row as it is and increment the column. Alright, that's what we are doing in the code, and eventually we need to add it, right? We need to add the sum of both the paths, right? So that's exactly what we are doing here. All right, now we also need to think the base conditions where we want to stop our recursion call stack to go further. For example, when we reach at 2, 0, we cannot go towards the down because it will go out of the matrix, right? We need to stop. So here is the base condition when we go out of the matrix, and from here we just simply return 0 because there is no path possible from this state. All right, now there was one more base condition was there, that is when we reach to the end of the matrix. All right, we need to stop here because we find the one unique path, we need to return from here, right? So here's the base condition for that, and here we just simply return 1 from it, that we have found a solution. All right, so yes, that's it. This is a solution for the backtracking. All right, now we need to convert this solution into the dynamic programming solution. All right, so for the dynamic programming solution, we need one more matrix, as we discussed, one 2D matrix where we want to store our outputs, right? So let's define it. Okay, now in the now at the end of our recursion call stack, and when we started giving the output, we need to store the output somewhere, right? So that we can check whether we have already computed that subproblem or not, right? Whether we have already computed it or not. All right, now here we are just storing the output of the subproblem into the 2D DB matrix where row and the column represent some output, right? Now we are done with the storage. All right, now one more thing is left, that is we need to check whether the output or whether we have already computed the a subproblem again already or not, right? So here's the code for it. Here we are just checking if we have some value, if dp row and column is not 0, that means we have already computed some output, so we will simply return that output instead of going further. Or you can say it is also one kind of base condition or the constraint where we are stopping our path to go further. Alright, so that's the simple solution, simple tweak that we need to do for the dynamic programming solution. Alright, so here's the code for the dynamic programming solution. So guys, we are almost done with the video. If you really want me to cover some more examples related to top-down dynamic programming approach, please let me know in the comment below, because I understand that understanding approach from the single problem statement is not easy, right? It's kind of difficult, and that's why I have put some questions link into the description below. That questions are kind of similar to this problem, so that you can understand this approach better. If you have any query related to this problem or any problem, please let me know into the comment below. I'll reply to every single comment. Alright, so guys, yes, we are done with this video. If you really like this video, please give it a thumbs up and subscribe to my channel. That helps me and that motivates me more to grow this channel. Alright, so thank you so much.